12.2 straight line motion. Right now what I would like you to do is just pause the video and read through the notes of 12.2. So there's 2 pages there. I want you to read those and then we'll talk about the ideas. So kinematics is the study of straight line motion, and it forms a very small part of the study design, so I won't delve too deep into it. As you can see by reading your notes, it looks fairly complicated, but it's not so bad. The idea of displacement. So displacement is simply the distance that an object is away from an agreed origin. So there might be a certain position. It might be in the Cartesian plane, so it might be position 2, 3, or it might simply be the staircase in a practical example. But there's an agreed origin, an agreed reference place, and displacement is how far an object is away from that agreed origin. The velocity of an object tells us how quickly it is moving. And the acceleration of an object tells us how quickly that object is either picking up or losing velocity. And this has lots of practical ideas related to calculus. So let's look at each of the definitions. So displacement, it's given as x of t. So we use x to represent displacement, not x the variable, and we use t as in time. So the displacement can be shown for any given amount of time. It's simply the distance that the object is away from an agreed origin. Velocity, v of t, can be seen as being the rate of change of displacement. So how quickly has the object changed displacement in comparison to time? Or simply change in displacement over change in time. It's a derivative of displacement. So if we take our displacement function and work out its derivative, that will be equivalent to the velocity function. And we can write that as dx dt, change in displacement over change in time, or x prime of t. So simply put, your velocity is equal to x prime of t. Now acceleration. I told you at the very start that it's simply how quickly an object is picking up or losing velocity. We write acceleration as being a of t. It's the rate of change of velocity. It's the change in velocity over the change in time, the derivative of velocity. And we can write that as being v prime of t. We can also say that acceleration is the second derivative of displacement, and would write that in this format. It means the second derivative of displacement. And that makes sense because we know that the derivative of velocity is equal to acceleration, and we also know that velocity is equal to the derivative of displacement. So in other words, if we start with a displacement function, to get the acceleration function, we take the derivative of displacement to give our velocity, then we take the derivative of that the second time to give us our acceleration. So that's why we can say that the acceleration function is simply the second derivative of displacement. So these next 3 graphs show us displacement, velocity and acceleration. They're quite useful. The first graph, we're looking at x of t. So we're talking about displacement and time here. Notice that the time is in seconds and the displacement is in meters. So this is in fact the x of t function, all right? The in brackets on a graph just means that the unit of measurement is in fact meters. But we're looking at displacement versus time. Now, given that the velocity is seen as being the rate of change of displacement with respect to time, then it's clear to us that the slope of this displacement graph tells us the velocity of the object. So interestingly, you can see we have a turning point here. Here we have a zero slope, so therefore the object is at a zero velocity. It's not moving. Here we have a constant section, so therefore the velocity of the object is constant. It's moving at a constant rate. Here in this section you can see it's increasing, so it's building up velocity. In this section it's decreasing, therefore it's losing velocity. In this section here, then you can see that it's completely flat as time goes by. That tells us that the object is at rest, it's finished. We also have the velocity graph. Now remember that we've got v of t. This is just telling us the units of measurement, meters per second for velocity, but it's the v of t function. And here we have time. And what's interesting for us here is that acceleration is the rate of change of velocity with respect to time. So again, what you can see is that the slope of the graph tells us something important. The slope of this velocity graph tells us the acceleration of the object. So here you can see that it's increasing. All right, so you can tell there that the acceleration of the object is increasing. Through this section, it's decreasing, so therefore the acceleration of the object is decreasing, and here we are increasing. And of course here we are just flat, so therefore the object is neither accelerating or deaccelerating. And let's look how that compares with the acceleration graph. So we've got a of t, the units are meters per second, and we've got time. And as you can see here, between this section the velocity is decreasing, therefore the graph is deaccelerating. It has a negative acceleration, and that's shown in the acceleration graph. In this section here, you can see that the graph is increasing, and that means that because if the velocity is increasing, it must be accelerating, and therefore we are shown the acceleration as being above the time axis. And the same thing applies over here, where we have it increasing, and therefore the acceleration is positive. Notice through this section here, the graph is parallel with the time graph, so the velocity is parallel with the time graph, which means that there is a zero acceleration, and therefore that's shown here. So you can see how each of the graphs are interrelated. So we'll go through that with a little bit more detail in class, but as I said to you, don't stress too much. It's a very small part of our study design. In problem 1, we're looking at the displacement of a particle traveling in a straight line, and it's given by x of t, which means displacement, equals 2t cubed plus t. Now, there's a typo in your notes. That should be 2t squared plus t. So if you just change that, that'd be great. Where x is in meters and t is in seconds. Our first job is to find an expression for the velocity. So v of t, velocity, is going to equal the derivative of displacement. And if we look at our displacement function, remembering that's squared, then the derivative of that is going to equal 6t plus 1. B, find the velocity of the particle when t equals 5. So I'm going to take my velocity function, 6t plus 1, sub in 5, and that will produce 31 meters per second. C. Find an expression for acceleration. So the acceleration is going to equal the derivative of velocity. Velocity we've already worked out as being 6t plus 1. If I take the derivative of velocity, it's just going to be that constant 6. D, what is the acceleration of the particle when t equals 5? So I'm now going to have a of 5, and it's equal to that constant, meters per second, or if you like, 6 meters per second squared. Problem 2 here, this very nasty person decides to drop a hammer onto a crowd of people. The height function of the hammer is given as h of t equaling 5 minus 0.15 times t squared. We need to work out the height, velocity and acceleration of the hammer after 2 seconds. We then need to also work out how long it takes for the hammer to land on the floor. So here's our h of t function. When we think about this hammer, it's only moving in a straight line, up and down. So it's straight line motion. And this h of t function could be easily written as x of t equaling 5 minus 0.15 t squared, where x of t represents the displacement of the hammer. Firstly, let's work out its displacement after 2 seconds. So we need to substitute 2 into the h of t function, or the x of t function, to produce 4.4 meters above the ground, because it's positive. What's its velocity going to be? Well, let's work out a velocity function. So v of t for velocity is going to equal the derivative of the displacement function. Now the displacement function is the same thing as the h of t function, the height function. So if we took the derivative of this, you could see that it's negative 0.3 t. We now substitute 2 into the velocity to get negative 0.6 meters per second. It's heading down. And then finally, a of t, the acceleration, is going to be the derivative of the velocity. Now, given that the velocity function equals negative 0.3 t, if I take the derivative of that, I'm going to get negative 0.3. So that will be a constant acceleration. So it's negative 0.3 meters per second squared. How long does it take to hit the floor? Well, we assume that the floor is at 0. That's our reference point. That's our agreed point of origin. So we've got h of t equaling this. I make it equal to 0, and I solve for t. Notice that I can do that using CAS, and I'll get 5.8 seconds. Now, we didn't say that this is an example that would have been on Earth, but you could also assume too that perhaps this hammer may have had some kind of parachute on it. So it took a long time. There was, obviously going to be gravitational pull, so that would mean that the hammer would fall quite quickly. But if it had a parachute, that would be an opposite force to it, and so therefore perhaps overall the the hammer was not falling as quickly as we would expect because of the parachute. What's most important here is that you understand the mathematics of how you can relate displacement, velocity, and acceleration. You know that acceleration is simply the derivative of velocity, and velocity is simply the derivative of displacement. That's the most important part to understand.